Okay, so this week um, we have 5 problems in this set, and some of the problems, if you have looked at them already, you might notice that they're a little bit easier than last week. I'm kind of trying to figure out where the difficulty should be, especially for the beginners. But anyway, I do have at least one problem that's a little bit harder, but even the easy problem, hopefully, you'll still learn something. All right, so the first problem, it's called solving for carrots. Again, I assume that you have read the problems. So there's some story. You have a number of contestants in this contest and a number of these Hufflepuff problems that people have solved. And each Hufflepuff problems um, need to give you a reward of 1 carrot. And then you have to figure out the number of carrots that you have to hand out. The input has 2 numbers first. First number N is the number of contestants, and then P is the number of problems that are solved in total, and then these N people with some line that's a kind of description of themselves, and then you have to output a single integer, which is the number of carrots that are handed out. Now notice that it doesn't ask you how many does each person get. You have no idea who solves how many problems, because in this problem, all you care about is the total number of problems solved and the total number of carrots taken given out. So I don't know if this is a trick question or reading comprehension, but at the end of the day, turns out that all you have to do is to read the second number, which is the total number of problems solved, and just print it. You can ignore everything else. You don't even have to read this input because it doesn't matter. So all you have to do is read the first 2 numbers. You have to read the first one because otherwise you can't get to the second one. And then, well, you just print the second number. So I don't know if there's much to say, but I'll show you my code anyway. Maybe I don't have this. Oh, okay. I guess I didn't even bother saving it because it's so simple. Uh, anyway, I guess I'll do it. So here it is. Just because they have this extra input of names, you don't actually need to read it because you never use them anyway. So uh, I think that's it. Let me just confirm that we actually. Uh-oh. Oh, did you see? Because I did it too fast. I only read in P. I forgot to read in both of them. Okay, that's kind of embarrassing, but um, okay, this time it will work. Oh, okay. All right, so let's look at something a little bit more challenging. Okay, quick brown fox. So pangram is a phrase that includes at least one occurrence of each of the 26 letters A to Z. And you're probably familiar with this the quick brown fox jumps over the lazy dog. It has all 26 letters. So your job is to recognize pangrams. For phrases that don't contain every letter, report what letters are missing, and we'll say that a letter occurs if it occurs at either uppercase or lowercase. So you have to basically uh, pretend that uppercase and lowercase are the same. Starts with a line N, which is next how many lines to follow. Each line has a single phrase. It has upper and lowercase letters, spaces, and other things like digits and punctuation. Each phrase contains no more than 100 characters, but at least one. For each input phrase, I'll put the word pangram if it qualifies as a pangram. Otherwise, say which ones are missing. And the list of letters that are missing should be reported in lowercase and sorted alphabetically. All right. So There are many ways you can do this, of course, but of course, what I want to show you is how you would use the standard library to help you solve this a little bit more efficiently. And also, what else do I want to say? Um, yeah, what else do I want to say? That we want to be able to use some of the standard library stuff. So let's get to it. All right. So the first question perhaps is, how are we going to keep track of which letters are seen and which letters are not seen? Because this is basically the point of this whole problem. Okay, so I'm going to write the standard int main. And the first line is an integer n, which is number of cases. And then I'm just going to loop with a function, and then the function would solve each particular case, like this. Now, the next thing to do is to read the next line, right? We have to read one line at a time, and because there's spaces, you got to use a get line, like this. Now, before we do anything else, if this is what we're going to do, we already lost. Okay, so why is that? So you have input like this, 3, and then a bunch of stuff, a line, and then you have maybe another line, and another line, and so on, right? So when we do C in N, it's going to read this stuff, this 3. But when you read C in or N like this, it's going to read until you no longer have a digit. And what you don't realize is that there are invisible characters, the \n, at the end of each line, like this. So after you read in the integer n, it's going to get rid of this, and now the input cursor is kind of hanging here. And now if you were to say get line, what it's going to do is it's going to say, okay, grab me until the next end of line. But because you're already at the blank end of line, the next thing it's going to read is a blank line. And then the next time you read the next line, it will read this one, sorry, and up to here, and then here, and so on. So what happened is that the very first line, if you read 3 lines after this, the very first line is a blank, and you never get to here because 1, 2, 1 line, 2 lines, 3 lines. So basically every time if you were to use this extraction operator to read formatted input like this, with integers or anything else, it's always going to hang at the end here, right after whatever you read. And if you were then to mix it with get line, you're going to read this blank line accidentally. So what you have to do is that after you do this, but before you actually start doing your line input, you need to call this one extra time to get rid of that hanging new line. So let's go back to here. So right here, we better call this once. And of course, I need a string variable to do that. And now we are safe. Okay, so this is something that it's commonly missed when you first learn about how to do line-oriented inputs, especially if you mix it with this type of input. Okay, so now that we have this, what are we going to do? Okay, we're going to have an array that I'll call present, and I'll initialize it to auto false. And this is going to tell me if a letter is present or not. Now in C++, technically, if you have 26 things, you should do this 26 times and write false 26 times to initialize. However, in C++, you're allowed to only put 1 or 2, and then the missing ones are not automatically filled in with whatever you have. They are automatically filled in with zeros. So this, the way I wrote it, is equivalent to writing like this: 26, and then fill it all the way to 26 entries. And 0 is false. So that means that this actually initializes everything to false. Now, if you try to do this, it won't set everything to true. It will set the first one to be true and everything else to be false. So this is a shorthand that will do it. And this is a shorthand that doesn't work. Maybe you don't like this kind of tricky code. This will be clear because you can just fill the 26 entries to false. Okay, so I'm going to have 26 array elements to say whether something is in there or not. So what am I going to do now? I'm going to say for every character in the line, so this is a line is a string is a container of characters. I can use a range-based for loop to loop through all the characters. And now I got to make sure that I keep track of whether they are in there or not. Now, I only care about the uppercase and lowercase letters, and anything else, digits, spaces, punctuations, I don't want. So how am I going to do this? I can say if it's alpha ch, then do something. Okay, so if it's not alphabetic, so this is alpha is a built-in C++ function that checks if a character is an alphabetic character, then what do I do? Well, I want to look at the character. I want to make it lowercase or uppercase. So maybe I just change it to lower. So everything is lower. And now the letter is between A and Z lowercase. And if I were to take the ASCII code of little a and subtract, this will turn it into a number between 0 and 25. A will be 0, Z will be 25. Because in ASCII code, these 26 letters occur in a sequence. So when you just do an ASCII code arithmetic, this will allow you to convert the character value, which is the ASCII code of the character, to the number 0 to 25. And then I can say present equals to true, like that. Okay, so this will take the character, ignore it if it's not alphabetical, convert it to lowercase, and mark it in my array as being there. And that will process the whole line. And now what do I do? Now I have to decide if everything is there. So how do I know if everything is there? There can be a number of ways, but basically I need to make sure that everything in the present array is true. So one way to do this is if present, I can use the count function in STL, which counts in a container how many times something occurs. And in this case, I'm asking how many times true occurs. If it's exactly 26, then that means everything is there. Otherwise, something is missing. So, oops. So what do? Cout missing, lowercase. And then I'm going to check, right? So I'm going to say for I equals 0, I'm going to try one by one. If not present I, then I want to print a character corresponding to I. But how do I do that? Well, it's going to be the character A plus I, and that would be back to the character. But if you do that, that won't work because it's thinking that these are numbers. So you can convert it back to a character. This is a way to convert this number back to a character. And then at the end, I'm done printing all the things that are not present, and I can print the new line. Okay, so there are a few things here. I mean, the actual algorithm, I guess, is not that bad. I mean, you just process all the characters and remember which ones you've seen. And then at the end, check if you've seen all of them and print out the missing ones. But I wanted to show you a few different techniques, different STL commands or functions that you can use to help you do your job better. And of course, also this tricky business of mixing this type of input and then line oriented input and make sure that you don't accidentally read a blank line that you shouldn't have. Okay, so let's accept. So one of the things that you'll probably notice if you look at my solutions or watch me do these things, is that I do use STL functions like fill, its alpha, to lower the count fairly regularly. It's usually good practice to learn these functions and do and use it. I mean, you might say, well, why not just write a loop? This is pretty easy. Like fill is pretty easy. It's true, you can write a loop, but uh, when you use a library function like this, not only is it perhaps easier, and then there's less chance of you accidentally making a typo. It's also more descriptive, right? You see the word fill, you know what's going on. You see the word count, it helps you understand your thought process a little bit better. That's the way I normally think about this. Okay, so next one, combination lock. Okay, so basically you have this combination lock. They tell you that you have to turn the dial clockwise 2 full turns, stop at the first number of the combination, and then you turn your dial counterclockwise 1 full turn, blah, blah, blah. So you have to read this to see how this combination works. If you have one of those physically, you probably have used this and you know what's going on. And then if you're given the initial position of dial and the combination of lock, how many degrees in the dial is the dial rotated in total, both clockwise and counterclockwise when you open the lock. And it's between 0 and 39. So I guess the first thing is to remember that a full circle has 360 degrees. There are 40 ticks. So 360 divided by 40 is 9. So each tick is 9 degrees. So you can either keep track of degrees or keep track of number of ticks multiplied by 9 at the end. So it doesn't really matter. We'll just, okay, so I'm actually not going to show you code, but I want to show you the process of how to do this. Okay, so 0, 1, 2, dot, 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 39. Okay, so at some point, the initial one may be here, and then maybe the first number is, I don't know, 25, let's say. So initial, and then first is 25. So what are you supposed to do? Remember that the very first step is to spin it twice, right? That's the very first step that they say. Turn the dial clockwise 2 full turns. So that's immediately, uh, if you're counting ticks, it's 80. If you're counting degrees, it's 720. So that's step one. But no matter what you do, you always have that. Now you have to turn its dial which way? Turn the dial counterclockwise 1 full turn away. Okay, turn this and stop at the first number, but you're dial clockwise. Okay, so we're turning this way. So in order to figure out how much, so we did our 2 turns, and now we have to go from 2 to 25. So the number of ticks you have to do. So first step is simply 25 to 2 minus 2, which which is 23. Okay, but is it always that easy, right? So what if whenever you have a circle, right, 25 minus 2, that's easy because 25 minus 2 is 23. But what if you are going from 25 to 2, right? If you just use this same formula, I'm going to end up with 25, 2 minus 25, which is negative 23. And that's not what I want. I don't want negative numbers. And so how do you deal with that? Well, whenever you're doing this kind of circle arithmetic, this you can use small j arithmetic. There are 40 ticks here. So this is basically like 42. 2 and 42 are the same. And if you do this, you will end up with 17, right? Now, if you did do the 22 minus 25 and you get the minus 23, what do you do? If it's less than 40, if it's less than 0, you just add 40, and that gives you 17. Okay, so basically, you know where you're supposed to go, you know where you're from, subtract where you need to go by where you come from, and if it's negative, you add 40. Okay, and that will give you your the number of ticks you need to get the first number. Okay, then turn the dial counterclockwise 1 full turn, so that's another 40 ticks. Continue counterclockwise until the second number is reached. Okay, so let's imagine now that we're still doing 25 to 2, but this time we're doing counterclockwise. Okay, so counterclockwise, you can't just do 22 minus 20. You can't do 25 minus 2 because that's the wrong way. So how do you do this? Well, if you want to go counterclockwise from 2 to 25, that's the same thing as 25 to 2 clockwise. So basically, you do the same thing that we did before, except that you flip the start and the end. Okay. And then finally, you turn the dial clockwise again until the third number is reached. So you do the same thing. So as long as you know, right, how to do clockwise, right? So if I want to go from start to end clockwise, what do? The number of ticks is n minus start, and if negative, plus 40. And if I want to do start to end counterclockwise, then I just compute n to start clockwise. So you only have to know how to do clockwise turn. If you can do that, you can do counterclockwise as well just by flipping them around. Okay, so I'm not going to write the code in front of you. And here's my code. So I read in the 4 numbers, the start, the first, the 3 ticks. And in this problem, it says if you keep doing it until they give you 4 numbers that are all 0. So basically, this is a loop that keeps trying to solve a problem. The first thing that you do is you read the 4 numbers. If they're all 0, you quit the loop. You quit the function and you return false to quit the loop. Okay, so how many do you have to do? So first, I'd make 2 full turns. And then here, I do something a little bit different, but it's almost the same. So instead of subtracting and then deciding whether it's negative, I check if it's going to be negative first, and then I either do this or I add 40 in my subtraction, and then at the end I multiply by 9 to convert to degrees. Now you may not have seen this notation before. This is what is called ternary expression in C++. It checks if this first condition is true. If it is, the result is this next one. If it's false, then the result is this. Okay, so this is the first number. Then I do one full turn, so that's 360. And then I do the counterclockwise. So I do the same thing, but I flip things around. So that's that's why this was in the other direction. And then I do the third one, and then at the end, I'll put the angle. Okay, so I'm not going to do this in front of you from scratch because I think it's just a matter of doing the calculations carefully, of course. All right, Friday the 13th. All right, what is Friday the 13th? This planet, Friday the 13th, is a lucky day. You are going on the spaceship, blah, 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 and calculate how many times Friday the 13th happens in a year. But the calendar changes every year. Every year starts on a Sunday, but other than that, they change everything. They have released a list of calendar specifications of the next few years. A calendar specification consists of the total number of days in the year, number of months, the number of days in each month. Task is to figure out how many times there will be Friday the 13th based on the calendar specification. Okay, so what do you have? T is the number of test cases. Each of T cases has D and M, total number of days and number of months, and then M numbers, which are the number of days in each month. Everything is at most 1,000. Okay, so what should we do? Because everything is 1,000, it is okay just to try every single day, right? So you start from day 1, day 2, day 3, day 4, all the way up to whatever days I give you. Because you know this is a Sunday, then the next one has to be Monday, Tuesday, Wednesday, and so on. And actually, it's better, to be honest. We usually like to uh, start counting at 0. So instead of 1 to D, I'm going to go from 1 to D minus 1. And then Sunday, Monday, Wednesday, Tuesday, Wednesday, Thursday, Friday, and Saturday. And then it goes in a cycle of 7 days, of course. And if the day it's one of these, then Fridays are always D. When you divide by 7, has a remainder of 5. That's what Fridays looks like. But you also have to make sure that it's actually the 13th day of a month. So how would you do that? Well, you can just keep track of month and day, right? Month, this is a month and day. So the beginning is, again, we'll just use 0, 0, 0, 1, 0, 2, 0, 3, and so on. Now, if your month has, I don't know, 30 days, then at some point you will have 0, 29 like this. And then if you, instead of going to 0 to 30, you have to, I guess, carries by changing this to a 1 and making to 0 and start all over again, right? So it's just a matter of moving from one day to the next, keeping track of incrementing the day. And then if it gets too big, you set it back to 0 and increment the month. And anytime that you have a Friday and the day is 12, don't use 13 because we are counting base 0, then you have Friday the 13th. Now, you might say, well, this is kind of, I don't know, inefficient just by going one day at a time. Why don't we do, I don't know, 7 days at a time or something else? Or maybe a whole month at a time, right? For example, if I know, let's say I'm counting the number of days from the beginning, so I know that days 12 is the first 12 of a month, right? So month 0, day 12, this is my first 13th of the month, and I can check that day is also 12. So that's Friday the 13th, Friday the 13th. And then maybe that month has 30 days. So to get to the next month at day 13, all you have to do is add 30 to get to 42. And that means that 40, I guess you call it January 12, January 13. No, wait, sorry, February 13 because I'm using one base. So this is a second month, 13 day. It's 42 days into the 43 days into the year. And you might say, well, it's much faster just to add the number of days in that month to move to the next one. And that is true unless one problem. The one problem that you have is what if the number of days in the month is less than 13? And then you could be in some trouble because now you're no longer matching the 13th day of that month if the number of days in the month is less than 13. So you could adjust for that, but then the adjustment in the calculations and so on is quite messy. So you might as well just simulate one day at a time because there are only 1,000 days. So let's see. So here's what we have. We have number of days and okay. So again, the number of cases. So I generally read the number of cases and then just loop that many times. For each case, I read the number of days and number of months, then reads in the number of days in each month. Everything is zero based. Okay. Number of Friday 13th that I counted, so far zero. Current day and month of the calendar, make sure that I use zero based. And then I just loop through all the dates, all the days in the year. And if the current day is 12, which means it's 13th of a month, and it's a Friday, then I add one. Okay, so this is a little bit of a tricky construction. You might normally say if this is true, add one. But this is a Boolean condition that if true translates to one and if false translates to zero. So this is a way I can just write this code without actually using an if statement. And then I always increment the day. But if it gets to be the number of days in the month, then I reset the number of days, the current day to zero and increment the month. Then of course, because I'm using zero based, I reset if it ever reaches that number, not one more, but when it reaches exactly, and I always have to do pre-increment. I increment first, and then I check if I reach the overflow for that month. And that's how I solved that problem. Okay, so the first four problems I hope are not too difficult, at least algorithmically. I mean, you might take a bit of time to work through that if you're doing it yourself, but they should be fairly straightforward. If I would say Friday 13, maybe it takes you a little bit of time to, or maybe you wouldn't be able to come up with the approach that I took. And if you go down the wrong path, you could, in fact, get into a lot of trouble. But if you do the right path, it shouldn't be too bad. Of course, you still have to implement it carefully. The last problem, it's one that I would say fairly standard kind of questions that they would ask you in 3620, although they probably would not ask you to code it. And they probably wouldn't phrase the problem in this way. So this problem will require some extra knowledge that you need from at least 2620, if not 3620, to do this problem. All right, so let's see what this problem is about. In this problem, you have to analyze a particular sorting algorithm. The algorithm processes a sequence of n distinct integers by swapping two adjacent sequence elements until the sequence is sorted in ascending order. For the input sequence 91054, it produces the output which is sorted. Your task is to determine how many swap operations ultra quicksort needs to perform in order to sort a given input sequence. input sets were aligned to contain single integer n, which is up to 500,000. The length of the input sequence, each of the following n lines contains a single integer between 0 and 999 million, which is the ith input in the sequence element. Print a single line containing integer number of OP, the number of swap operations necessary to sort the given input sequence. Okay, so the only thing that you're allowed to do is swap two adjacent sequence elements. That's it. You're not allowed to swap things that are not next to each other. So it depends on how much sorting you know, but the first thing that you might recognize is that if you think about all the if you think about sorting algorithms, one of the algorithms that they use swapping adjacent element is bubble sort. Insertion sort also can work that way, but not selection sort. The selection sort requires you to possibly sort swap things far away, and then quick sort and merge sort and whatever other sort you might have learned probably requires you to swap things that are quite far away. So we're looking at things like bubble sort or insertion sort, which you may or may not remember. But no matter whether you remember or not, you should know that these are slow sorting, which has n squared time. So what does that mean? That means if you just implement one of these things and just count how many times you swap adjacent elements, this is going to take n squared time. It's 500,000 for n, and that would be way too long. 500,000 for n square, it's way too much. So that's no go. We can't do this, but we should still know what kind of algorithm we're looking at. So we need to know how these slow algorithms would work without actually simulating these slow algorithms. All right, so let's look at I don't know. You have a bunch of numbers that are in the array, and let's say that you look at these two numbers that are adjacent, and they are in the correct order. Would you ever want to swap them? The answer is no. If you swap them, then it actually doesn't really help you at all. Eventually, you have to undo that swap. If they are in the wrong order, then you probably want to swap them at some point, but maybe you don't swap that to a particular pair because you might want to swap other things, and then eventually you swap. They're no longer together, and then you swap some other things. Okay, so how do we think about this? There's a concept about permutation called inversions. Inversions means that I look at any pair, not just adjacent. I look at any pairs of numbers in my permutation like this, all of them, right? So all the things that starts with a 3 for the first position. And I look at which one of these are out of order. So 3 and 7 are not out of order. 3 and 2 are out of order. 3 and 1 are out of order, right? But the rest of 3 are okay. What other ones are out of order? 7 and 2, 7 and 4, 7 and 5, 7 and 1. 2 and 1 are out of order. 4 and 1 is out of order. 5 and 1 is out of order. 10 and 1 is out of order. So if I count how many are out of orders, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the number of inversions, it's 10. Okay, so let me just erase some of this. and just be a little bit clearer with exactly where the inversions are. So one inversion here, one inversion here. Then I have 4 inversions here, and then 4 more like this. Okay, now what is the reason why we look at inversions? If you have an adjacent pair and you decide to swap them, what can happen? Well, if you have this pair that was in order, in the right order, and you swap them, you will increase the number of inversion by 1. If you have a pair that is out of order and you swap them, you decrease the number of inversions by 1. This inversion. If this is 6 and 4, right? Oops. If this is 6 and 4, there's an inversion here, and you swap them, you will decrease the number of inversions by 1. Now, there could be other inversions here. There could be 10 and there could be 2. So this is an inversion, and this is an inversion, and this might be inversion. But by swapping these two, you will not be able to change the inversion from 6 to 2 because 2 doesn't get involved in the swap and 6 doesn't move across 2. Similarly, 10 and 6 and 10 and 4, those inversions cannot be changed. And of course, 10 and 2, you're not touching either of them, so that's still an inversion. So when you swap adjacent pairs, the number of inversions go up by 1 or go down by 1. Always. And then if you have a sorted sequence, right? If everything is sorted, 1, 2, 3, 4, 5, 7, 10, how many inversions do you have? 0. There's no inversions. That's the definition of a sorted sequence. So what does that mean? Each adjacent swap, if you swap two things that are out of order, decreases the number of inversions by 1. If you start with 10 inversions and every single swap can only get you down by 1, you must do 10 swaps. And 10 swaps will always work because if it's not sorted, there must be an adjacent pair that is not in order. So you can swap that to decrease the number of inversions by 1. So whenever they test you, how many adjacent swaps do you need to sort something? It is actually a question of how many inversions you have in a sequence. That is exactly the same question. Okay, so that's the first breakthrough is we want to count inversions. How do we count inversions? Well, I guess you can just look at all possible pairs in a double loop and see if they're out of order. But if you do that, then we're back to n squared again. So we have to do something better. By the way, what is the maximum number of inversions you can have? If you have a sequence that's completely sorted backwards, then every single pair, it's an inversion. And in that case, it's n choose 2, which is n times n minus 1 over 2. And that is actually important because in our problem, n is 500,000 at most, and n times n minus 1 over 2 actually will overflow a 32-bit integer. So whatever you do in this computation, make sure you use 64-bit integers. Otherwise, even if you compute the number correctly, you need the right data type to store the result or you'll be wrong. Okay, so now how are we going to compute inversions? And this is a classic thing that you may have seen in 3620. Um, so I'm just going to go talk about it. You have an array of stuff, and you want to know how many inversions there are. So the standard algorithm for this problem, it's a divide and conquer merge sort algorithm. So if you have seen merge sort, hopefully you know what this is about. So what do? Well, first of all, if your array that you're trying to sort has one element or less, then you don't do anything because it's already sorted, and the number of inversions is 0 because there can no be, if there are no pairs, there cannot be inversions. Otherwise, you split it down the middle in half, and then you recursively sort both sides. Now, in terms of inversions, I can also get the number of inversions on the left and the number of inversions on the right. And those are the inversions on each side. And then I have to say, well, how many pairs across the two halves are inversions? So merge sort would take these two sorted lists. I don't know, 4, 7, 8, 12, 15. And then maybe on the other side, there's another sorted list. 6, 9, 10, 13, 16, let's say. And it will say, okay, let's look at the beginning of each half. The one that's smaller goes into the bigger list, the sorted list, right? So 4 is less than 6. So 4 goes in here and be here, like this. Now 4, because it's the smaller of the two, and it comes on the left side, there are no inversions from about 4 that crosses into the other half. Because 4 is less than 6, so 4 is less than 6, 9, and so on. The next one, though, so set 4 is taken care of now, 7. The next one here, it's smaller, so I have to merge the 6 into here. But now I need to know that there's a whole pile of inversions here. How many? Everybody from 7 and on, it's an inversion with 6. So I figure out how many there are here, in this case 4, and I realize that there are 4 inversions. Now I look at 7 and 9. 7 is the next one. Whenever I pick something on the left, I don't have to update inversions. Next one is 8, so I don't have to worry about it. And the next one is 9, and now I have to update the number of inversions by 2 because there are 2 left on this one. So every time I pick something on the right, I need to update the number of inversions by the number of things left on the left-hand side. And that's basically what you have to do. So you would do merge sorts using, if you have seen merge sort or program it before, or at least seen it in class, you basically use that algorithm or use that code and then add in the bookkeeping for the number of inversions every time you pick an element to merge from the right-hand side. So I'm going to show you my code. Again, I'm not going to go through the quick sort code. The merge sort code. This is maybe hopefully standard, but I have this function called inversions, takes a vector by reference because I'm sorting at the same time, and then the start and end indices of the sub array that I'm sorting at the time. And I remember to return a 64-bit integer if the number of elements that I'm sorting is 1 or fewer, there's nothing to sort, and the number of inversions is 0. Look at the middle, then I recursively compute the number of inversions on the left, on the right, add them up, and then I do this merge. How do I do this merge? I have a temporary that stores, so this is my temporary here, to store the merge result. I have an counter to keep track of how many inversions I have. And then I1 and I2 are basically my indices of the beginning of the two halves. And TI is the index into my temporary to write to. And basically, I just keep checking as long as I haven't run out of both lists. If the one on the left is smaller, then I just move it into the temporary. Otherwise, I move the run on the right to the temporary, but then I got to update the number of inversions by the number of things left on the first part. And then when it runs out, when one of the lists runs out, you have to make sure that you copy the other one, the remaining elements of the other one, and then you copy it back from the temporary back to the original array. So this is, if you've seen merge sort, this kind of code is fairly standard, I hope. If not, then you probably want to look into this. This is a standard algorithm that's taught in 3620 and sometimes 2620. But this is a way to compute the number of inversions using merge sort. And as you know, merge sort is n log n times. So the complexity is much better than n squared, and it will be fast enough. Okay, so this one is definitely more algorithmic compared to the other first four. You actually need to know something to do this problem, but it would be a good exercise to try it. Even though I've already told you how to do it, you might want to just no, don't just follow along the video to type your code, but turn it off and try to do it yourself and see if you can get this done. Okay, so that's it for this week's video. So I'll talk to you guys next week.